Start.
Okay, today I'm going to be presenting from the AP test problem from 1988 mechanics problem number 3. Okay, so in this problem we have two uniform disks that have equal mass and each can rotate on frictionless bearings about a fixed axis through its center. The smaller disk has a radius of r and the bigger disk has a radius of 2r. Problem A is asking us to find the moment of inertia of the larger disk about its axis in terms of I. So, we know that I is equal to simply mr squared. And in this case, since the radius is 2r, we can say that I is equal to m times the quantity of 2r squared, which leaves us with m times 4r squared.
Why?
Which makes this 4mr squared. And since we know that mr squared is equal to I, we can say that this is 4I. Now, for part B, we have to find the angular acceleration of the larger disk. So, the best place to start is with the rolling constraint, since it says that the light chain is not slipping. So this is essentially a rolling with slipping problem now. And we know that the rolling constraint is V is equal to omega times r. Now we know that the velocities of both of these disks are equal. So we can say that V1 is equal to V2. So omega 1r is equal to omega 2r. Now, using our rotational kinematic equations, we can say that omega is equal to initial omega plus alpha t. And since it starts off with no rotational velocity, this will go to 0. So we know that omega is simply alpha times time. So now we can say that r1 times the angular acceleration of the first one times the time is equal to r2 times the angular acceleration of the larger disk times t. And we also know that r2 is simply 2 times r1. So we can say that r1 times alpha 1t is equal to 2r1 times alpha 2t. Now, both of these r1s cancel out, and the t's cancel out. So we are left with alpha 1, which is equal to 2 alpha 2. So we know that alpha 2 is alpha 1 over 2. Now for part C, we are asked to find the tension in the upper part. Now this is a different problem actually. So the diagram shows the two disks with a cord around them. So now we are asked to find the tension in the string on the top. So the best place to start is with a free body diagram. So we know that the only force applying a torque on this system will be the force of tension. And let's say let's set our fulcrum right in the middle. And we know that this distance here is 2r. And let's make this the traditional, conventional sign convention, with counterclockwise being positive. So now we know that if we write our sigma tau statement, it will be equal to I alpha, which is equal to 2r times ft. Now, we solved earlier in part A, we know that the moment of inertia is 4I, and we know that the angular acceleration in terms of the angular acceleration of the smaller disk is alpha 1 divided by 2, and this is equal to 2r times ft. Don't need this equal sign. Okay, so now when we simplify, we get that 2I alpha is equal to 2r ft, and when we solve for ft, the 2's cancel out, and we get I alpha over r. Now for part D. Here we are asked to find the torque that the student applies to the smaller disk. So let's draw another free body diagram of the smaller disk. And the force applied is this way. Force applied. And there's also a tension force in the opposite direction. To keep things consistent, we need to make sure we have the same sign convention. Now, the force applied is going counterclockwise, so this will be the positive one, and the force tension is clockwise, so it will be negative. So when we do a sigma torque statement, it will be equal to the torque applied minus the torque of the tension, so R Ft, which is equal to I alpha. Solving for the torque applied, we get it is equal to I alpha plus R Ft. Now, we solved for Ft earlier. We know that it's I alpha over R. So with quick substitution, we get that torque applied is I alpha plus R times I alpha divided by R. Now the R's cancel, which leaves us with I alpha plus I alpha, which means that the torque applied is 2I alpha. Now for the final part. We are asked to find the rotational kinetic energy of the smaller disk as a function of time. So we know that rotational kinetic energy is 1/2 I omega squared. And using our rotational kinematics equations as we did before, we established that omega is alpha times time. Now with basic substitution, we can get that this is equal to 1/2 times I times alpha t whole squared, which leaves us with 1/2 I alpha squared times time squared. That is problem 1988 M3. Thank you.